What I just did was the long way around to find the wave equation. But there, and I did it that way because to me, that makes physical sense. You just think about, oh, I changed the field in this region, it gives rise to a circulating field. And then working it out just gives you an idea as to where that wave equation comes from. But I have another way of doing it that is the, let's say, the mathematician's preferred way.
Yay!
We know that.
I thought it was divergent to B
in the
is 0.
absence of charge, either magnetic or that's a 0. Either magnetic or electric charge. Our Maxwell's equations look like this. Gauss, Faraday, Maxwell, Ampere. So just by using vector identities and rather simple vector calculations, we can arrive at the wave equation. What I'm going to do is take the curl of this. Why? Because it works. Curl of both sides. Right. I'm going to use the vector identity. Curl is a little neater. Oops. Gradient. What do I want to say about that? That's my reference.
Because Schaum said so.
Is that divergence of E is 0. So my left-hand side is del squared E vector, minus del squared E vector. Left-hand side. Right-hand side, I've got curl B, which is minus 1 over C squared, E squared, U T squared, E, making this substitution there. Done.
And then,
Wait a minute.
wait, how do you get?
Got a minus sign.
No, that's right.
That's right. Yeah.
Because then you also can do it from the del inversion. Can't you?
Yes. But I'm going to go with 3 vectors.
Why? 4 vectors are so much more fun.
Why is why is there a C squared on the bottom?
It's MKS units.
What? Oh, let me see. I had a C here. Oh, and I plugged that in. And you're right. It disappeared, didn't it? Wait a minute.
You didn't disappear. That's
Curl is 1. No,
that seems consistent. I'm checking.
I think that's MKS units.
No, it isn't.
That's gas units?
These equations, Ryan can check me, in the front of the book. Yes, Calvin.
Why are you allowed to use 3 vectors and not 4 vectors if light is moving relatively?
Because the
I'll get back to you on that. Because it gives you the same answer. Good question.
Because it was done this way before people...
With that?
sounds a little bit silly and.
I haven't thought about it.
You do have the time change.
You do have, you
Yeah, it is
effectively.
a four vector.
It's just a different way of writing the four
You
vector.
just, that's the time coordinate, that,
Yeah,
I
that
included it explicitly.
yeah.
that is.
So
four
it's
vector.
essentially you're taking like the Laplacian of the E4 vector or whatever
No, that's
equals
just the four
0?
vector. That is just the four vector. It's just writing it a different way.
Okay, so if we straightened out where the c squared comes from, or doesn't come from, according to what I've written here.
That is right.
That's, oh, you know what? That c squared is there for every one of the wave equations.
It should be because it should be one of v squared.
Basically just
It's the speed of light. It's gotta be in there.
the four vector.
It's there.
It's just this.
I'll say it loudly one more time. It's there.
So that's like the D'Alembert.
All right,
Yeah, I know that's-
so, we have an expression for the electric field then. Which is obeyed by each of the components of the electric field. And there are actually lots of solutions to that. We'll go for a general solution that we can use to express a whole lot of other solutions.
That looks like second cosine function.
If we, oops, just think about solving this as a scalar field, right? The form of the solutions is going to be the same. It's just that ultimately I will need to include a prefactor which defines a vector direction. But if I just were to write this and say, let's look for solutions to that, all right, then those solutions look like this. I can maneuver around the pluses and the minuses in there, but they're going to correspond to wave traveling one way and a wave traveling the other way. By putting in a vector r and a vector k here, I'm going to allow the vector to be traveling in any direction locally. Right? So the magnitude of k is going to be frequency divided by the velocity. Or for us, square root of mu epsilon. In MKS, I would just use mu naught epsilon naught. Well, actually, mu epsilon would be fine, just the way it is, the absolute value. In CGS, you use the relative permittivity and permeability. So that's
In your general equation, should CV squared.
there. Since I have a vector solution that I'm looking at, the electric field, so the reason that I wrote that is because I expect that that's familiar to all of you. Yes? How many of you? If you've had quantum physics, you've done that. Okay. But now, if this is a vector, then those guys become vectors. That's basically it. But I'll rewrite this in a slightly different form, which is that it's an amplitude times a vector direction in which the field points. I'm just going to choose some direction there. Times actually, I have to be a little bit more careful here. Let me go back. When we're talking about measurable fields, here, measurable electromagnetic fields, they're actually going to be sines or cosines, not e to the i's. So what we're actually doing is we're, for example, taking the real part of that, in which case I would be taking cosine kx minus omega t. All right. Any vector directions will be real, so I can pull them out. And so now I can rewrite this as an amplitude. Actually, I'll use amplitude A. Nope. A vector direction for the first, for the wave. It's going to be pointing in some direction. A e to the I a dot r minus omega t plus. If I allow myself a phase, okay, sorry. This corresponds to all the possible solutions going in two directions, right? Plus propagation in R, minus propagation in R. If I confine myself to solutions which are propagating in one direction, so that's what you're accustomed to us calling a plane wave, just traveling along in strictly one direction, then this becomes a vector direction for the field, and then this is propagating in some vector direction k, and so k defines the actual propagation direction for the wave, and this propagation is in the plus kr direction, right? If I have the minus sign over there, the minus minus, that will be in the minus kr direction. And I have still screwed up. E1 real part of that. Okay? And the electric field is going to be, the magnetic field will actually be related to the electric field. So I can write the electric field, let's say, as E1 hat, real part of an amplitude A, E, and my magnetic field is going to be directly related to that. Actually, I'll write this as E0 here. And the magnetic field could be pointing in another direction. We're going to look at the relationships that have to hold there now. Real E naught e to the I. They're both solutions to the same wave equation, so the forms of the solutions are going to be the same. And then I have the relationship E naught is equal to the square root of mu epsilon E naught. So that's what my solutions look like. And there, yes.
One thing I've always been curious about, why are the magnetic fields and the electric fields in phase with one another? It seems like since they're related to...
Derivatives.
Yeah, that they would be...
Except that one's a derivative in space and the other one's derivative in time. But both of them are derivatives.
Yeah.
And I troubled myself about that as a student. Actually, I read it about your state, and a little bit later saying, shouldn't they be out of phase with each other? It just seems reasonable, given that argument that I just gave you with throwing the waves.
Exactly.
Right? But the arguments are, let's say, completely symmetric.
Okay.
Number one, you can say that, right? And one's a derivative in space and the other one's a derivative in time.
Right.
And since you're taking the derivative of a sine function or of a cosine function, you do see that, you know, if I started with the electric field being a cosine, then I have to have the magnetic field be a cosine as well. I haven't answered your question, but it seems not unreasonable that the arithmetic leads to that. In
Another.
a deeper sense, I don't know.
Okay. Yeah, it also seems odd that, like, as if you look at the wave in time, you just have a pulse. The energy and the propagation of the wave seems like it's always bunched up in areas.
It's there and then it isn't.
Yeah.
Yeah, it is that way.
They're called photons.
No,
Oh, no?
well, no, the photons are spread over space and time.
Ah.
No, but what he's talking about is the local field. And there's a field here
Right.
and not here,
Yeah, if you're
and
only
here,
looking at one.
and not there, here, not there.
And
And that is true, that's the case. The whole thing moves along.
Right, okay, so you can actually see the sphere
Yes. Can we see it?
or measure it.
we can barely measure the B field, so.
We can beat fields against one another and in pulses. And we can see the oscillations. Jesse?
Do these two